Welcome to Klein's Calculus. Today we're going to look at a related rate problem. Related rate problems are when you find out that two things are changing and they're related to each other. And they're changing over time. So we're going to be differentiating with respect to time in these cases. Now, when you do these things, I've found it's much easier to keep your thinking organized with a nice organizer like this. We're going to step through it together, and we will look at this problem from the book, Example 2, in Lesson 4-6. In this example, a hot air balloon is rising straight up from a level playing field, and it's tracked by a rangefinder 500 feet from the liftoff point. At the moment, the rangefinder's elevation is pi over 4. The angle is increasing at the rate of 0.14 radians per minute. And the question, the thing we're going to try to find is how fast is the balloon rising at that moment. So our first thing we're going to do, we want to see what's going on. So we're going to draw and label a picture. So we come over here, and I'm going to put my balloon right here. I'm not much of an artist, so that's all you get from me. And here's my ground, my horizontal distance of 500 feet. And right here is the rangefinder. And I know that, and we can see as the balloon rises, this angle is going to increase to keep track of it. So this angle is changing as the height of the balloon changes. Okay? Now I can't put anything about the angle being pi over 4 degrees here, and I can't, or radians, excuse me, and I can't put anything about the height or the rate the angle is increasing, because that's something that's only true at the point in time. So I'm going to put theta equals pi over 4 right here. And I'll put that the change in the angle over the change in time is 0.14 radians per minute. Because that's information that was given to me, but it's only true at that point in time. What do I want to find? I want to find, and we say it in words, how fast is the balloon rising? At the moment in question. Because that balloon might have started off real slow and be going up faster and faster. We want to know at the moment that the angle is pi over 4, how fast is the balloon rising. And if you think about that, and you want to write it in variables too, that would be the change in height over the change in time. So that's what we're looking to find. What information do we know that is not going to change? Well, we know that horizontal distance, 500 feet between where the balloon lifted off and the rangefinder, that's not going to change. But that's all we got here. Now to write an equation to relate the variables, that's often the trickiest part. And we have to think, what variables do we have here? Well, I've got a height that's changing, and I've got an angle that's changing. And I have this handy little 500 down here. So trig identities come to mind, because you know you got a nice right triangle and an angle and some numbers. So I would think a good relationship might be the tangent of theta equals the height opposite over the adjacent. So I'll write the tangent of theta equals height over 500. And that's my relationship between my variables. But we want to differentiate with respect to time because we're looking for how things are changing. So now I'm going to take my tangent, and the derivative is the secant squared. And we know, because we're taking it with respect to time, it's going to be the secant squared of theta times the change in theta over time. And that's going to equal 1 over 500 times the change in height over the change in time, because that would be our derivative of height, of h. Now that I've done that, we want to solve for dh dt, because that's what I'm looking to find out here, is the change, how fast is the height changing. So I'll multiply both sides by 500 to get 500 times the secant squared of theta times the change in theta over time equals the change in height over the change in time. Once you've done that, plug in this moment in time information and simplify. Plug in moment in time info and simplify. So I'll write 500 times the secant squared of pi over 4 times 0.14 equals the change in height over time. And now I've got to think, okay, how do I do the secant squared? Well, coming back to my nice 90 or 90 degrees 45 or pi over 4, I know I've got 1 square root of 2 for my ratio. I know the cosine and the secant are reciprocals. Cosine is the adjacent over the hypotenuse, so the secant is the hypotenuse over the adjacent. In this case, square root of 2 over 1. So I'll write 500, and instead of square root of 2 over 1, I'm just going to write square root of 2 squared. 0.14 equals the change in height over time. Well, the square root of 2 squared is 2 times 500 is 1,000. Multiply that by 0.14, and that's your change in height over time. Well, we know that multiplying by 1,000 means move the decimal 1, 2, 3 places to the right. So I've got 140 equals change in height over the change in time. I've answered my question, but we must always give the solution in sentence form. And that's where it's kind of nice, and we need, of course, units. To get my units, I'll look, and it's height over time. So height's going to be measured in feet because the horizontal distance was measured in feet, and time's going to be measured in minutes. So I know I've got 140 feet per minute is going to be my change in height over time. So to answer my question, I think, what was the question being asked? That seemed a while ago. And I come up here to where I see it in words. And I say, to answer it, at the moment in question, the balloon is rising. So that's what I'm going to write. At the moment in question, the balloon is rising at, and I put in my answer here, 140 feet per minute. And we are good to go. So hopefully this is going to be of great help to you. Just a quick recap. Start by drawing your picture. Write down what you need to know in a sentence and in symbols. Put the information, the distances, the measures that don't change here, and you can use those when you write an equation. Things that are changing as time goes on, you put in this box, and you do not use until after you've taken the derivative. Find a relationship, sometimes the trickiest part. Take the derivative with respect to time, so you make sure that you've got your change in angle over time and change in height over time. Solve for whatever you're looking to find. Get it on one side of your equation. Now you can plug in your moment in time information, simplify down, remember units, and then just answer your question. At the moment in question, huge, don't forget to say that. The balloon is rising at, here's your answer, 140 feet per minute. So hopefully this is going to help you, and you're going to have as much fun doing these as I do. So enjoy your problems, and see you in class.